Welcome everyone. Today I'm going to present my master thesis work, which I've done under Professor Lucas Lomriser in the past one and a half semester approximately. So the topic of my research was star formation rate across the multiverse. Um, I basically studied the Bousso-Leichenauer model, which is designed for varying parameters. So basically, it's for multiverse, not only applicable in our universe, but it can be applicable across the multiverse. So the overview of my presentation would be a short introduction of what star formation rate is, then the introduction for the Bousso-Leichenauer model, then the assumption used in it, and then the couple of equations which build up the BL model, then results, and some of the references which I have used. So what is star formation rate? And why do we study star formation rate? Star formation rate is a key parameter. It understanding the galaxy formation and evolution. And in layman terms, it's the total mass of stars formed per year, which is of course described in solar masses per year. And we don't directly measure star formation rate. First, we have to observe it in terms of star formation history and how stars have formed over time, how galaxies have formed over time, and then we study on a larger scale, on a scale of universe, and then we get a model for star formation rate. So the Bousso-Leichenauer model for multiverse. So it's actually a semi-analytical model to calculate the star formation rate as a function of time. Before this, we had a lot of models for star formation rate, but it were all experimental fits, simulations done, and it was not a proper theoretical model. So like we have the Einstein's theory of relativity, which theoretically predict that certain phenomena will happen, and then we experimentally observe it and we can verify the theory. But here we do not have a theory, so it's a step forward towards making a theoretical model for a star formation, to study star formation rate. The model can predict parameters in the multiverse if the underlying cosmological measures are known. I mean, in my case, what the study I have done, I basically the assumption is that all the universes which uh, underlie in my multiverse are all follow the Friedman equations. So it's a basic cosmological measure. So if that is known, then this model can be applicable. The goal here is not a detailed analytical fit, which I've already told, but it is to explain the observed value through a theory till some order of magnitude. For the same, we vary certain parameters by a larger order of magnitude. And like I said, models before this were already in existence, which were analytical fit. For example, the Hörnquist-Sprengel model, and so on. So my goal here is to get a basic understanding of the quantitative behavior of SFR as the parameters are varied. So what will I do is that I will vary the gravitational constant and study how it affects the star formation rate. And also, yeah, the extensions of the models are possible. So further parameters can be varied, and you can test the models varying the other parameters. So the basic assumptions in this model is that it's applicable to open, flat, and closed Friedman, Robertson-Walker universes. Considering other parameters fixed, we will vary certain parameters and observe its effect on SFR, and we neglect the feedback effects on the newly formed stars. So the star formation rate by the BL model and modifying G. So this is the final equation which the model gives, and this is the star formation rate that we get. So here the F is the cumulative mass function, P is the probability that halos uh, get virialized, so the probability that will get virialized at certain time. F of B is the baryon mass fraction. In our universe, it's approximately 1/16, and A is the parameterization factor, which is under root 32 by 3 pi. So there are, I mean, I will not be able to explain the whole model. It will take a lot of time, so I'll just condense it to the main equations, which are the building blocks of the whole model. So firstly, we use the extended Press-Schechter formalism and get a cumulative mass function. So this cumulative mass function F, what it what it defines is that the fraction of matter which resides in a collapse region of mass m at time t. Here the delta C is the critical density at which the halo collapses, and it weakly depends upon the cosmological parameters, so we neglect it. So yeah, the in short, let me explain the Press-Schechter formalism. Actually, it's the continuation or the advanced model of the spherical collapse theory, and here we consider a power spectrum of fluctuations, P of k, which is given in the variance in the second equation. So P of k is the power spectrum of the fluctuation, and the model predicts a number density of virialized systems of a given mass at any time t. So a mass function basically, and this power spectrum is like it is proportional to k to the power n. So where n is the scaling index, and in our universe it's around 0.960. So it's basically not linear after all. And basically the power spectrum is the, in other terms, if I can explain, it's the temporal evolution of the density fluctuation, which is equivalent in rescaling of the length scale, I mean the size of the halos. So it's like rescaling the halos, and when the density fluctuation happens. In general, the virialized structure that we get at time t VIR, it's approximately 1/6 of the initial co-waving size of the collapsed mass. And this variance, it is, I mean, it's a linear in theory. That's why we are able to separate the variables and write in terms of, it's a product of functions. So here Q is the primordial density fluctuation, S of M is a fit that is taken from the Tegmark paper, and G of T is a growth factor. So the G of the function G is a growth function, and which can be calculated using the this differential equation. And S of M is the analytical fit, which is taken from the Tegmark paper. And M of EQ is the mass of equality. I mean, at the mass of the halo at equality, radiation dominated and matter dominated. I mean, when the universe moves from radiation dominated to a matter dominated, so at point of equality, the mass of the halo is given by this. So this is the main equation, one of the main equations. So here the G is inversely proportional to M of EQ. So one of the main equations where G is varied. So next we get a star formation rate for a single halo of mass M, which is given with the first equation. It is basically M is the mass of the halo, FB is the baryonic fraction, and T of grav is the gravitational time scale, and the gravitational time scale is given by this. So I mean, if we look at the equation, we see that the gravitational time scale depends upon the gravitational constant, but it's not, because if we go into deep into the theory, we see that G is not effective in calculating in defining T gravitational time scale. So it looks like it depends, but it does not depend. So yeah, this can be calculated using the spherical top hat collapse theory of an avoidance region. It's a precursor of the press sector formalism. In short, it defines as a sphere of mass of any mass initially follows the expansion of a background universe. Then at some point it turns around and it stops moving in physical coordinates and it collapses down. So basically, we follow the Birkhoff theorem here, which states that we can consider some small part of the universe as an independent FRLW universe is the same cosmological constant, and we treat it as an independent universe, and the every other equations are applicable. So yeah, so the T gravitational time scale can be calculated from there. And lastly, there are two more important equations which are taken from Lacey and Cole, which are the probability functions. The probability functions is simply it defines a halo, probability of a halo that is collapsed when its mass is doubled. That's why we integrate from m/2 to m. And beta is some function which we use to define probability, and which is used as a differential in terms of a differential equation in that. So finally, we get the results here, and we see that as G is increased. So the first, let me give you a brief on the figures. So the first figure is for the G for the value of G is 6.6 into 10⁻⁻12. So it's one order of magnitude smaller than ours. And the middle one is for our universe, and then the right on the right it's for 10⁻⁻10, so one order larger. So we see that as the G's increase, the SFR peaks at a later time, and vice versa. It is because the mass at equality of a halo is inversely dependent on G, and when the gravitational time scale remains same, it doesn't depend upon G. So the mass of halos at equality is less for a greater value of G. Hence, it takes time for halos to realize, and hence the star formation rate peaks at a later time. So the peak of the star formation rate, as you can see, it shifts right as we go from lower values of G to higher values of G. Also, you can see that at zero. So what is zero? So the zero is taken as the time of equality. So when the radiation dominated era ended and the matter dominated era started at around 47,000 years after the Big Bang. So the photons were still coupled with the mass, with the baryonic matter, and there was no neutral hydrogen to form stars. So it decoupled around 300,000 350,000 years after the Big Bang. So till then, nothing, no star formation could have happened. So even though the matter dominated era started, the star formation rate couldn't have occurred till the decoupling and of course the recombination. It's also a question in cosmology that in our universe decoupling and recombination happens approximately at the same time. So after that, the star formation rate actually started. So therefore it's zero till certain times, and then it starts. So yeah, that was my master thesis work that I've done, and there are some of the references, some of them, not all, but some of the references I've used. So thank you.
thanks a lot for this very nice talk, Ishaan. Well, I see. Well, Daniele, is this a question or you're clapping?
I was actually clapping, okay. But I do have a question, if I may ask.
I should, yeah.
Thanks. Apologies if you hear a lot of background noise, but I'm in a public space.
Yeah, I guess you are on an airport.
Yes, I'm at the airport, correct. So yeah, thanks for the talk. Can you go back to the plots that you were showing, please?
Yeah.
So I followed your argument about how basically the gravitational time, if I understood correctly, would change when you alter G, and how that would impact star formation rate. But I think it's slightly counterintuitive to me that for much larger G, you would necessarily have less star formation, in the sense that I would expect that for a higher G, you have in general more clustering, so the halos would be more massive overall, and so you would have like more gas that can fuel star formation. So yeah, do you have any thoughts on that?
I mean, as far as I get, what happens is that at equality, the mass of the halos that are formed, that is less. So for star formation to happen, it takes a lot more time for mass to accumulate.
Okay.
For certain mass to accumulate. I mean, if I can explain that sense, for the same mass to accumulate to occur a star formation, let's say for a certain mass m star. So the mass of the halo is to be equal to m star. But at larger G, what is happening is that the mass of equality of that halo is less. So to accumulate that mass m star, it takes more time, because initially we have less mass of the halos.
Okay.
So that's what's happening here.
So yeah, you have a delay in the peak, and you also have a suppression of the overall star formation. I see. Yeah. Okay, thanks. Yeah, I need to go through the calculations myself at some point, but that's interesting. Thanks.
Okay.
Ishaan, so can you go back to this equation where you showed where G enters essentially for the mass of equality. So this is the only place where you've modified or let G vary, because I guess in other places it sort of gets absorbed.
I mean, for example, like here, like gravitational time scale, the G it gets observed in the theory, but for the mass of halos at equality, it explicitly depends upon G. Also, I mean, if I can, just a second, I've just forgot to mention the other parameters also. Just a second. So yeah.
So that was the key equation. Sorry to interrupt again. Okay, now I see it.
Yeah,
that's what you meant.
Yeah, it inversely depends upon G. Yeah, so the other parameters which depends are the minimum mass and the maximum mass. The limits which we excuse me, the limits which we exert on the mass of an halo in the BL model. So the minimum mass and the maximum mass also depends upon G. So it I mean, it doesn't really affect. I mean, if I see the theory, it doesn't really affect that much, because parallelly, if we see it parallelly affects the value of m minimum and n maximum. So it doesn't really affect.
But okay, so my question is presumably, so if you allow more than just one parameter vary, for here, for instance, you have the psi, right, which is essentially the matter density, and you could absorb. Would you get a perfect degeneracy essentially here between G and matter density, or will you change the matter density in a way that in another equation that degeneracy is broken? So in other words, can I, in your plots, can I just change the matter density and then move from one of the three plots you showed to another?
Yeah. Because so it depends explicitly. So at other places also, it gets. It gets defined, parallelly. So it doesn't affect other equations. Like if I substitute mass of equality in some other equation, so there the G will get absorbed or it will cancel out. So it doesn't really affect, because I tried most of the parameters, so it was not affecting that much. Also here the other factor xi, it's the baryonic mass fraction. So for this also I looked up the Fred Adams paper. He calculated the variation of it along with G, gravitational constant. So the variation was not that much. I mean, it was almost constant. I mean, for 2 or 3 orders of gravitational, increasing the 2 or 3 orders of gravitational constant, it was just like 1% 1.5% varying. So I took it like constant. Similarly, here f of b also it's constant, and yeah. Here q is also constant, probability density fluctuation. It doesn't really affect that much. So yeah. To answer your question, Professor, you can change the values of other constants. It will not affect.
Okay, thanks. Yeah. Any other questions?
Yeah, Ishaan, nice work, by the way. Can you move on to the result page? The result slide.
But yeah.
Yeah, over here you're like increasing the value of G gradually by one order. And like, can you just keep on doing that? Like, till what range you can go, like on and off from the G of our universe, and still end up with a working model of the universe, like the working universe.
I mean, where life could happen.
Yeah.
So yeah, I mean, for that we have to bring in the concept of fine tuning. So in fine tuning, we worked out that using in the Fred Adams paper that the values of certain parameters could not be increased or decreased by certain orders, because the universe will become inhabitable. From that point of view, I mean, universe will exist. There would be a universe with black holes, only black holes at some point of time.
If you like keep on increasing the G, it will only like have a big crunch of something like that.
Yeah, I mean, in the Fred Adams paper, there's a study of Q, the primordial density fluctuation with G. So yeah, if you look at that paper, you'll see that the values of Q for certain Qs are prohibited, because it will not have a habitable universe. So for that values of G, we cannot take. I mean, we could take, but the universe will not be habitable. Life would not be there. But yeah, a universe would exist. I mean, there would be a universe with nothing, only gas, no gravitational
if you decrease,
if you keep on decreasing
G too much. Yeah.
But the other parameters have to be, I mean, you have to check for the other parameters also.
Okay. And then the peaks of the rates will change accordingly, and then
I mean, if you see the left figure where the value of G is 10 to minus 12. If we keep on decreasing, there would be no star formation P. This means that there's no star formation happening in that universe for such a small value of G.
Okay. So that would be around like 10 power minus 15 if you go
Yeah.
or more.
I mean, I have not studied that case, so I could not tell at which value, but yeah, at certain value.
Okay. Okay. Good presentation, by the way.
Yeah, thanks.
So, any last question? Otherwise, Ishaan, thank you very much again.
Thank you. Thank you everyone for joining.